Okay, this is an introduction to confidence intervals for one sample means, and this will be just introductory information. So the reason we collect data from a sample is we usually don't know something about population, and we are forced to take a sample to use an estimate for the population of parameter of interest. However, if we're taking a sample and we're using that as an estimate, we're never able to say exactly what the population mean is. We can say it's about this or it's about that. In fact, you guys have already seen, because 2020 was an election year, you've already seen confidence intervals at work. Because how many times did you see something that said so and so has 47% of the vote plus or minus 3%? As soon as they told you it's plus or minus 3%, they were telling you it was a confidence interval. Now, they didn't tell you the value of the confidence interval. And we like to say that the confidence interval is comprised of two components, the estimate and the margin of error. So we have this formula, and it looks like this for what we're going to be doing right now. X bar, which is our sample mean, and that's our best estimate of the population mean. Basically, we went out and took a sample, we got an average, and we say, you know what, if you made me pick one number, this would be the number that I would say was the best. If I wanted to estimate the GPAs at Reagan, I take a sample, and let's just say I take a sample of 40 people, I average them, and I go, you know what, the GPA at Reagan is this. That would be my best guess. But that's only a specific, and you're like, well, how confident are you are that? And I'm like, well, I'm not sure. That's where this part comes in. And this part right here that I just boxed in is known as the margin of error. And that's where, when we saw the political polls, it was like plus or minus 3. So the GPA was 87 plus or minus 4 points. My error would be 4 points above, 4 points below. And there's one other thing that I need to address. This part right here is known as the standard error. And so basically, if I calculate this, I'm saying, and let's just say it was a 90% confidence interval. Well, if I calculate this, I'm saying I'm 90% sure that the true population mean actually lies within this interval. It may be in the center, it may be at the edge, but somewhere in there, I'm 90% sure that it's there. If I made a 95% confidence interval, I'd be 95% confident that it lies within the interval somewhere. Okay. Now, when I say I'm 95% confident that it's in there, that means I'm also 5% confident that it's not in there. All right. So 95% confident just means, hey, 95% sure that it's there, but there's a 5% chance that we didn't capture it, that we got a weird sample and we didn't capture it. All right. Need to talk to you about alpha. And alpha is the area in the tails. And basically, if we were drawing a confidence interval, and let's just say it happened to be a 90% confidence interval, we'd say 0.90 is here. That means the area in the tail would be 1 minus 0.90, which would give us 0.10. So our alpha would equal, in that case, our alpha would equal 0.10. But we have two tails. So that means in this tail, I would have 0.05, and this tail, I'd have 0.05. And together, those two alphas would form together to make, those two areas would form together to make my alpha. So the 0.05 and the 0.05 sum to give me my alpha of 0.1. Now just remember, alpha is 1 minus the confidence level. Please also remember that our confidence interval will always be centered on the sample mean. It'll always be centered on the sample mean. Okay. So there's several things that we can say. We can say we are 90% confident, or whatever our value is, our confidence level, could be 95, could be 99. We are 90% confident that the true population mean lies within the interval, whatever we captured. And that would be our lower bound and our upper bound. We can also say in repeated sampling, we expect this method will capture the mean whatever our confidence level was. So if our confidence level was 97%, we said we'd expect it to capture the true population mean 97% of the time. That means if we did this over and over and over again a million times to infinity, it would be 97% of the time it would work. That also means 3% of the time it doesn't work. All right? Key phrase. We are making a claim about the population mean and not the sample mean. So we're trying to estimate this. This is what we're trying to estimate. We actually know the sample mean. We calculated that, so we don't need to make a claim about that. As a matter of fact, based on the formula, it's the center of every single confidence interval. The sample mean will always be exactly in the center of the confidence interval, 100% of the time. All right? A couple other things. As we increase the level of confidence, like if we went from 90 to 95, the margin of error or spread increases. In other words, the interval is wider. All right? So as we increase the confidence level, the interval gets wider. As we increase alpha, the interval narrows. So if you increase the confidence level, it gets wider. We increase alpha, it gets narrower. All right? And as we increase the sample size, the interval widens. All right, once again, here's what we can claim. 95% confidence the true population mean lies within the interval. We can also claim 90% of the intervals collected by this method will capture the true population mean. Again, whatever our confidence level will go here. All right? Here's a list of things that we cannot claim. All right, we cannot claim. The main thing I want you to get out of that list is do not use probability, do not use chance, do not use likelihood. Use the phrase confidence. All right, use the phrase confidence. And also remember, while we're 90% confident that it worked, that means we're 10% confident that it did not work. And you're going, well, I want to be 100% confident, and so do I. But unfortunately, we're using a sample to estimate the population, and samples are not going to be perfect because they don't represent the entire population. So consequently, there will always be some error. So we'll never, ever be able to say with 100%. All right, moving on to the next page. All right, so I want to go back and review some interval stuff that we've previously done because we're going to build on this. And typically we said the area, if we said calculated a z-score and we went in an area of 0.68, we were talking about this area right here, and we'd say plus or minus 1 standard deviation. But I want to go about and calculate the exact value. All right, I want to calculate the exact value. So second vars, inverse norm, area, and since we're centered on 0, and this is really key, we're centering on 0, we're centering on that x bar, we're going to go parenthesis 0.68, excuse me, parenthesis 1 minus 0.68, close parenthesis, divided by 2. And since we're working for a z, our mean is going to be 0, a standard deviation is 1, and we end up getting negative 0.944. So this is negative 0.9944. And by symmetry, I know it's going to be positive 0.944 because we're centered on 0. And I'll go ahead and do that real quickly for that one. Second var is inverse norm. And I'm just going to come back and add 0.68. Oops. Plus 0.68. And I go back and I should get positive 0.944. So by symmetry, this is going to be the same. So let's do the same thing for 0.95. Second var is inverse norm. And this is going to be clear parenthesis 1 minus 0.95, close parenthesis, divided by 2. Since it's a z, mean is 0, standard deviation of 1. And we end up getting negative 1.9599. So a lower z of negative 1.9559. 9.59. And we'll have by symmetry, 9.1599, and an upper Z of 1.9599. So that's my upper Z. If I'm doing my area for the 0.997, second vars, inverse norm, clear, parenthesis, 1 minus 0.997 divided by 2. Now, we said by empirical rule, this is essentially plus or minus 3. You can see it's not really 3, but it's close. So we have negative 2.9677. Because we're symmetric about 0, and it's critical that this be about 0, this is going to be 2.9677. Like, okay, Mr. Spencer, I remember how to do that, but why is that important? Well, I'm glad you asked. So let's do this, but let's no longer center it on 0. All right, let's no longer center it on 0. Let's center it on 3. We'll keep it centered on 0, but let's change our standard deviation. Instead of 1, let's make it 5, and let's make our sample size 4. So here's what we're going to be doing. We're actually going to be sitting there going, all right, 0 plus or minus our Z star, which we're always going to make positive. It just makes life easier. Just make it positive, times 5 divided by the square root of 4. So let's do that real quickly. So 0 minus 0.9944, we're going to do the negative part first, times 5 divided by 4, the square root of 4, so all right? And so this gives me negative 2.486. All right, because it's symmetric about 0, I should get positive 2.486, so let's do that. 0 plus 0.9944 times 5 divided by the square root of 4. And I get positive 2.486. Now, I don't know about you, but I'd be really happy if there was a shortcut method to that, and there happens to be. So let's go stat test, and we're going to look for Z interval, which happens to be number 7 on the calculator. So we're going to look for number 7 on the calculator, stat test, Z interval, highlight the word stats, so it looks like that. Well, what was my standard deviation? Oh, it was 5. The X bar, we're supposed to be centered at 0. My sample size, 4. My confidence level is the same as my area, so that's going to be 0.68. And guess what? It did the work for us. All right. It basically calculated that Z star that we did right here, and it did all this work for us. So let's do this instead of showing all of our work, which we could, let's go back and just change our confidence level and go second vars. Stat test. And we're going to go to number 7 for Z interval. And now we're just changing our confidence level to 0.95. And now we find that we're centered at negative 4.9 to positive 4.899. All right. Now, technically, symmetry, they should be negative 4.9 and positive 4.9. So there's some rounding in there. So now let's do the next one. So stat test, Z interval. And we're just going to change our confidence level or an area to 0.97, 0.997, I should have said. And we get negative 7.419 to 7.4193. Now, if I go ahead and keep the same standard deviation that I have above, so I kept these standard deviations the same, and I kept the sample size the same, but this one was the upper one was centered on 0, this one's centered on 3. And you're going to notice that our interval shifts, all right? Our interval shifts. So let's do that real quickly, all right? Let's see what happens when we change that stat test, because it's a lot faster to do stats test. We go to number 7, which is z interval. And now our x bar is no longer 0. Our x bar is 3. We kept our standard deviation the same at 5. We kept our sample the same as our sample size at 4. We're changing our confidence level to 0.68. And now I get 0.513 to 5.4. So 0 is no longer exactly in the 0 is no longer in the interval. All right, we shifted this thing up because we shifted it up and had a positive mean of 3. So now my interval is 0.51386, comma, 0.54 or 5.4861. If I do it for 0.95, stat test, z interval, number 7. All I'm going to do is change this, and it's going to be 0.95. And now it's going to get a little bit wider because we want 95% of the data. This one had 68%. This one's going to have 95%. So we now have negative 1.9, comma, to 7.8999. Now, if I were to average those out, if I were to find the midpoint should be at 3. So the midpoint of that should be at 3. And the midpoint of this one's at 3. So half this way and half that way. All right, so x bar is 3. This would be net 0.51. This would be 5.4. This would be negative 1.9. This would be essentially 7.9. And this is negative 1.9. Right here would be the 0.5. And I'm just rounding these because I don't have room. And this one would be the 5.4. Doing it one more time, for the 0.997, stat test z interval, which is number 7. We're going to change this confidence level to 0.997. And I end up getting negative 4.4 and positive 10.4. All right. So 99.7% of the data lies between here, 95% lies here, and 68% lies there. We can do the same thing changing the sample size. And watch what happens when we change our sample size. When we change our sample size, we said on the previous sheet, my interval should get narrower. So let's go ahead and do this again, but let's see if our interval gets narrower. So stat test number 7, z interval. We kept the standard deviation of 5, the center at 3. Our sample size is now 16. And we need to start off with a 0.68. When we do that, I end up getting this value is 1.75. And I get this value is 4.24. All right. 3 is still my middlemost number. 3 is still stuck in the center, so that hasn't changed. However, my lower point is not quite as low as it was over here. Here is at 0.5, but now it's only to 1.75. My upper point is not quite as high. This one is higher, so this one is further spread out than this one. So this is narrower. And if we do this for 95%, stat test, z interval number 7, and we're just going to change that to 0.95, and this becomes 0.55 is my lower bound, and my upper bound is 5.45. Compare that to when we were at negative, and here we're not negative yet. Here we're at negative 1.9, but over here we're still positive. Up here, we were all the way almost at 8. We were at 7.9, and here we're not even to 6 yet. So this one is definitely narrower, and it's narrower because we're dividing by our sample size. finally, second vars, oops, stat test, I keep doing the second vars, stat test number 7, and we're do the 0.997. Now we're finally negative. We went to negative 0.709 and positive 6.709. Once again, this thing, well, this was all the way up at 10.4. This is at 6.7. So obviously this is lower, and this is not quite as low over here. So this one is narrower. 99.7% of the data lies here, 95% lies here, and 68% lies here. So the idea behind this is the center will always be X bar every single time. As you increase your Z star, it gets wider because we got wider. And as we increase our sample size, we got narrower because we went from here and we got narrower over here. All right, looking at the recipe for success, and I'm just going to tell you, we're going to talk about this very, very briefly. All right. Very important that you follow this step by step. All right. And you can have this while you're taking a test, and it'll help you out. And college students are all the time asking me for these. Define the parameter mu in context. For us, it's going to be you're going to always start off, let mu equal the true population mean. Always start off with that. Conditions. In regular statistics, we're not going to worry about the conditions, so you can just write assumed. In other words, we believe that they were met. Write the formula. Well, here's our formula. X bar plus or minus Z star, sigma divided by square root of n. If you'll notice, that's what we were working with on the previous page. So nothing has changed here. If they give us data, we have to enter through stat edit, and I'll show you directly how to do that. Make sure you list all your parts. So you're going to write your standard deviation, you're going to write your sample mean, and you're going to write n. Okay. We have to calculate Z star, which is where we're going to do the second var's inverse norm 1 minus. And since it's calculating a Z, mean is 0, standard deviation of 1, and just use the positive value. Use the positive, it just helps. All right, then we're going to go stats test Z interval, which we were previously doing, and we're going to follow these steps. Write the interval, whatever it is, and then we're going to write our conclusion. This is our confidence level. 95% confident that the true population mean 4. This is where you're going to put in number 1. You're not going to write number 1, but whatever you wrote for the definition, you're going to write there within the interval. And this came in from problem part number 8. All right. Explain the meaning of the level if asked. In repeated sampling, if we do this over and over again, we expect that this method will capture our definition. We restate the definition again, and then we're going to restate our confidence level. And that's the step-by-step process of the confidence level, and we're about to take on and work one in the next video.